So finally, in this video, we are going to solve for the temperature. So to start off, what we're going to need is our actual moles of hydrogen and carbon. So we are going to be using our balanced equations that we made, and we will be doing a matrix multiplication. So to start off, we are just going to enter what is given to us about the moles of the fuel. So I'm just going to call this like N fuel. And this will be an array. It will be 0.95, 0.04, and 0.01. And then, like I said before, we will be doing a matrix multiplication of those values multiplied by the ratios of the carbon and hydrogen in each of the methane, ethane, and propane. So I'm just going to call this like the atom ratios. And this will be another array. And the first one will be 1, 4. And then 2, 6. And then 3, 8 for our propane. So now we can do our actual matrix multiplication, and that will be using the @ symbol. And what this is going to be giving us is, it will be giving us an array that will actually be equal to our moles of carbons and hydrogens. So we can actually unpack this into our moles of carbon and our moles of hydrogen. And all this right here is supposed to be one array. Like that. So now, using these moles of carbon and moles of hydrogen, we're going to use that to get the moles of our other species, the CO2, H2O, O2, and N2. So first and easiest is CO2, and it's just going to be a 1-to-1 ratio with our number of carbons, or moles of carbon, because in both equations, here we have 1 mole of carbon and 1 mole of CO2, and then here we have 2 moles of carbon and 2 moles of CO2. So for our moles of CO2, that's just going to be equal to our moles of carbon. And next, for our moles of H2O, that will just be equal to our moles of hydrogen divided by 2, because over here we have 4 moles of hydrogen, and here we have 2 moles of H2O, so 4 divided by 2 is 2. And then in this equation, it's the same thing, where we have 6 moles of hydrogen divided by 2 would be 3 moles, and we have 3 moles of H2O. So for our moles of H2O, that will equal just our moles of hydrogen divided by 2. Now this is where it gets a little more complicated. So for our moles of oxygen here, it looks as though it's just in a 1-to-1 ratio with, oops, let me just refresh that. So it looks like it's in a 1-to-1 ratio here from the oxygen to the H2O, but if we look in the second equation, that is not the case. So what it is actually is, with our 2 moles of oxygen over here, we can get that from dividing our moles of H2O by 2, so that would be 1, and then adding our moles of CO2. So 2 divided by 2 is 1, plus 1 is 2. So then we can check that to see if that works here as well. So 3 divided by 2 would be 3 over 2, and then plus 2 for our moles of CO2. That would then get us our 7 over 2 for our moles of oxygen. So how we're going to type that in is it's just going to be our moles of CO2 plus, and I'm just going to put parentheses here to be safe, we are moles of H2O divided by 2. And finally, our moles of nitrogen. So for nitrogen, all we really need to know is that it's in that 79 over 21 ratio to our moles of oxygen. So we can just do the moles of oxygen times 79 over 21. And then one final thing that will also come into play here is for our moles of oxygen and nitrogen, we need to remember that in the problem, they told us that it will be in 20% excess air. So that air is going to be including oxygen and nitrogen. So to account for that, I'm just going to add a little thing in here for our excess air. And it said it was 0.2. So we can just add that. Multiply by that, and we're going to add 1 to our 20% excess air, like so, in order to account for that amount of oxygen that will be in that excess air. And then since it's doing that for our oxygen, it would then also apply to our nitrogen because we have this in here for our nitrogen as well. So I'm just going to run that. So now we want to define our moles going in and our moles going out. And how we're going to do this is we're going to have to combine 2 arrays, first with our moles of each of our fuel components, methane, ethane, propane, and then another array with our moles of these values here. So how you combine arrays is numpy concatenate right here, and so we will be combining our N fuel with another array of our moles of O2, our moles of N2, and then it would be our moles of CO2 and H2O, but since this is what is going in, we don't have any of that going in, so it's just going to be zeros. And then now for going out, we can just make another array. But this time we won't have any of our fuel values going in, so those will all be zeros. And then we will have our moles of oxygen. But again, for our moles of oxygen coming out, we're going to need to multiply that by our excess air value. And then again, our moles of nitrogen is coming out, and then our moles of CO2 and moles of H2O. Like so. Now finally we can define a function that we're going to be using the root solver for, or on, to get our temperature. And we will be inputting a vector into this function. And our vector, or the first index of our vector, is going to be equal to our temperature. Like so. So what we will be returning will be a difference between two dot products of our enthalpy function times our moles out at the temperature that we are looking for, minus the dot product of our enthalpy function we calculated from before, times our moles in at the room temperature that we started at. So how we're going to type that into Python is we're going to return, and it will be a numpy dot for the dot product. And so we're going to start off with the enthalpy function at the temperature that we're looking for. And we're going to do the dot product between that and our moles out. And then that will be subtracted by another dot product between our enthalpy function, but this time at our room temperature that we were starting at, which was 298. And this time our moles in. And close off that parenthesis. Like so. So now finally we can use our root solver in order to solve for our temperature. So we're going to be using the root solver on our temperature function, and we need to supply a guess, which I'll just say like 2000. And I'm just going to run all just to make sure that this works. And right here, this x component right here will be our answer, 2051-ish kelvins for our temperature. And I'm just going to get that component out by doing .x. And then since it's an array, I can get the first component of that as well. And that will be our answer for the temperature of the adiabatic flame for this problem.